Yeah, hello there. So welcome to another session on the rapid prototyping applications in automotive industry. This is Dr. Samir, Assistant Professor in the Department of Mechanical Engineering in KITSW. So far we have seen the rapid prototyping applications in different industries. In the previous lectures, we talked about the applications of additive manufacturing or rubber prototyping, whatever we call. Uh, they, they imply the same. So we have seen these applications in the earlier classes in the field of biomedical industry, in the field of aerospace industry, in the field of the traditional industries such as joining, such as coining and jewelry. So we have seen all these applications. So today we'll be seeing about the applications of RP in automotive industry. Uh, this class we have already discussed through a video lecture from one of the sources through the internet. I've posted in the group to the students. So once again, to go through the contents, what exactly are presented in the prescribed textbooks of our syllabus. So I've come up with this short video lecture on the applications of RP in the automotive industry. So let's begin. The outcome of this presentation is that the student will able to understand different applications of rapid prototyping in automotive industry. And also he will be able to understand few examples of RP in the automotive industry, just like a case study, how exactly uh, they are being used in the automotive industry, we'll able to understand. So first, we'll talk about prototyping complex gearbox housing for design verification. So in any uh, automotive industry, the design verification has to be done. So to build a prototype is actually a cumbersome process. So in order to have less strain to build actual product and do the verification of design on the product, it's better to build a prototype. So RP comes in a hand in such cases. So here we have a typical example of rapid prototyping in building a complex gearbox housing, the design verification. Volkswagen has utilized Helicis LOM, that is laminated object modeling. So we all know that LOM stands for laminated object modeling, where the thin sheets are used here, and a laser cutting is used according to the contour of the design of the product which is being made in the CAD software, and it is transferred into the LOM machine. So based upon the contour, the additive manufacturing product is being obtained. So here, the LOM is being used as the RP model or method to speed up the development of large, complex gearbox housing for its Golf and Passat car lines. So especially the Volkswagen is a company, we all know it's automotive industry, it's a huge industry. So they were developing a complex gearbox housing for the vehicle which will be used in the Golf and the Passat car lines. So the CAD model for the housing was extremely complex and difficult to visualize. So the design of the model in the CAD was extremely complex and was difficult to visualize. So even though the engineers who design the CAD model, until and unless they see it physically, they cannot visualize what exactly the design looks like. So VW wanted to build a loam part to check the design of CAD model and then use the part for packaging studies. So they developed the model using the loam, again, they checked the design which was built using a CAD model, and then they used the part for the packaging studies. So using traditional methods, such a prototype would be costly and time consuming to build, and it may be always possible to include, it may not be always possible to include all fine details of the design. So one way to produce a prototype is to use a traditional methods. Traditional methods, you can use a subtractive method, or you can use an additive, or you can use the casting method, or any other method. But it would be definitely, it's a costly affair, and as well as it is a time consuming affair. So it may not be possible to include all the fine details of the design as well. So these are the three constraints. One is the costly nature of the prototype, the time factor, and the fine details of the design may not be possible to include. Then fabrication of the model based on drawings was often subjected to human interception, and consequently is error prone, thus further complicating the prototype process. So whatever the fabrication of the model is based on the drawing was often subjected to human interpretation. So human interpretations are basically complex, and obviously it will definitely lead to the error, and further it will complicate the prototyping process. So all these difficulties were avoided by using RP technology, as the fabrication of the model was based entirely on the CAD model created. The gearbox housing was too large for the build volume of loam machine. So, so whatever the difficulties that have arisen due to the conventional prototyping, so could be are avoided by using RP technology. And because RP technology, it creates the model based entirely on the CAD model. So CAD model is definitely a valid model. So there is no human perception, though there is no human interpretation of the things, which where it could go wrong, where it could create errors. But a CAD model, which is a valid model, using that CAD model, you can create the design. So that was the best part of using the RP here. The gear housing was too large for the build volume of LOM value. The build volume. So generally, whatever the machines that we use for additive manufacturing is very much less. Yeah, I think LOM is somewhat far better than the other processes such as SLA or FDM. But so even though the LOM has a good build space, but this gear housing was too large. So the CAD model was thus split into 5 sections and reassembled after fabrication. So what they have done is that, so they have split this CAD model into the 5 sections and reassembled it. It took about 10 days to make and finish all 5 sections. And once they were completed, pattern makers glued them together to complete the final product. So they divided into the 5 parts, they have assembled it. So all this process took about uh, 10 days. Law model was first used for verifying the design and subsequently to develop sand casting tooling for the creation of metal prototypes. So when they first initially used the law model, so they have used for the verifying the design. Subsequently, they developed the pattern using the sand casting toolings, and the RP process had shrunk the prototype development time from 8 weeks to less than 2 weeks. So generally, the time that has been consumed using a traditional one is around 8 weeks. So that has been brought down to 2 weeks, and considerable time and cost savings were achieved. So this is the best part of the rapid prototyping. Then another example, we can see prototyping advanced driver control system with stereolithography. In the previous cases, we have seen how the laminated object modeling was used. In this special case, we will be seeing the stereolithography. So another company at General Motors, in many of its divisions, RP is becoming a necessary tool in critical race to the first market. So whatever the manufacturing company, whatever they are producing, they want to bring it to the market. So who wants to bring it faster? So they are the market holders. So that's the scenario generally in the manufacturing sector. So to accomplish that, one of the handy processes is the rapid prototyping. For example, so Delco Electronics in its automotive electronics subsidiary was involved in development of Maestro project. So the General Motors, in collaboration with Delco Electronics, where they were developing the automotive electronics, where we can play the music, where we can have some controls. So the development of Maestro project. So the design to blend an advanced audio system. So as I said, so the major design was the major function was to design to blend an audio system, a hands-free cellular phone. So if any phone comes, if there is a phone ringing without engaging ourselves by touching the phone, lifting it, and uh, handling it. So instead of doing that, so hands-free cellular phone was integrated, and GPS navigation was also integrated, and radio data system information and the climate control. Nowadays, the climate control, what is the engine's temperature, what is the outside temperature, and what is the inside temperature, all this also being uh, controlled in the dashboard. So this is being done in the General Motors by using Delco Electronics. So they have come up with a project called as Maestro. Into completely integrated driver control system, then Maestro was to be a marvel. So this was a marvelous project that they have come up with, integrating all these wonderful add-ons. So this is a picture how it looks. These are the few an example which where I've come up in the internet. So I've taken it from the Maestro kit. This is been somewhat, it looks like the interior parts where you can have all the features. This is an electronic kit fitted to the car. Inside the car, this is a console where we can see, these are the touch buttons where you can control the, this is the climate here, and this is the HD radio here, and you have the audio system, and I can see if the door is open. Also, that is also been controlled. You can see, so all those things are clearly visible in the display panel here. So that was about one of the applications of rapid prototyping, where stereolithography, the console was made using stereolithography and with exact parts to be fitted. So they have used SLA there. So creating cast metal engine block with RP process. So another example to look forward for the RP applications in automotive industry is the creating a cast metal engine block with RP process. As new engine designs and development is an expensive and time consuming process, the ability to test a new engine and all its auxiliary components before committing to tooling is important in ensuring cost and time savings. So before developing any new engine and design, the development is an expensive and time consuming process. So ability to test a new engine and all its auxiliary components before committing to tooling is important. So that's what this RP is being doing successfully. So test it before going into the actual process. So Mercedes-Benz division of Daimler-Benz AG initiated a program of physical design verification on prototype engines using SLA parts for initial form and fit testing. So Mercedes-Benz has come up with a prototype of engine, especially the program was initiated for the physical verification of the design and the prototype using the SLA parts. So they wanted to check how exactly the form and what was the form and fit testing into the vehicle. So after initial design reviews, metal components were produced rapidly using the quick fast. This is one of the trademark processes. So after the reviews, they have produced. the metal components. So another example is that using stereolithography to produce production tooling. So production tooling, where we can use it for the master patterns. For example, here we have Ford Motor Company has used the 3D Systems Quick Cast to create the production tool of rear wiper motor cover for 1994 Explorer sport utility vehicle. So this was the one of the uh, one of the auxiliary item was manufactured by Ford Motor Company. So where they want to produce the rear wiper motor cover. The part measured approximately 200 mm into 150 mm by 75 mm and was to be injection molded with polypropylene during production. So all this was done based upon the dimensions given here. The traditional methods would have provided necessary tools for modeling in 3 months. So if you could have used the traditional methods, but that would consume around 3 months. But for the Ford first built SLA model of the cover and fit it over the wiper motor to verify the design. So dimension and assembly problems were identified and rectified before the design was confirmed. So using SLA uh, they could able to manufacture the cover how exactly it looks. If there are any flaws in this design, they could have rectified it before going for the actual production. So this is the figure which represents the cover of the rear wiper. So further going into this case study, we'll see another. So another method, what exactly they have done, we'll see. Okay, so this was about the production of the tooling for the rear wiper housing and using stereolithography to produce. Another example was that their first project was design and prototyping of 4-cylinder engine block for new Mercedes-Benz A-class car. So the aim was to cast the engine block directly from a stereolithographic quick cast. The engine block was designed on Mercedes-Benz own CAD system, and data were transferred to 3D Systems Technology Center at Darmstadt, where one piece pattern of the block was built on SLA machine. The full-scale investment casting pattern was generated in 96 hours. So in Mercedes-Benz, where the production of A class was taking, they want to build a new engine. So directly they have produced the engine from the stereolithography quick cast pattern. An engine block was designed there by using the data which was in the 3D systems, and they've transferred it to the SLA machine. And the full scale casting pattern was, especially investment casting, was generated within 96 hours. A using pattern was then sent for shell investment casting, resulting in 300 mm into 330 mm into 457 mm engine block being cast in A356 T6 aluminum in just 5 weeks. So the pattern, whichever that was produced by using the stereolithography, was used for the casting. And here another pattern, the shell investment casting the shell was created within around the blocks of 300 mm and 330 mm and 457 mm. And the material used was the aluminum A356 T6 aluminum was used, and within just 5 weeks, they could able to produce this engine block. The completed engine block incorporated the cast-in water jackets, core pathways, exhibited grade B radiographic quality in all areas evaluated. So this was not just a simple engine block. It was a very complicated engine block where they have incorporated the cast in water jackets. The passage of the water for the cooling purpose, generally they use core passageways, and also they have checked whether there are any any defects in the casting. So grade B radiographic quality in all areas were evaluated. The entire prototyping process using ARC technology lasted only 6 weeks. So compared to 18 to 15 to 18 weeks using traditional methods, it was done in 6 weeks. And the cost was approximately 1 lakh 50,000 was uh, compared with the traditional method. So savings was approximately $1,50,000 was saved using ARC technology. So these are both significant, especially in the need for short time to market requirements. So whoever wants to go first to the market, they have used ARC technology. So that's been the scenario ever since the rapid prototyping is being in the use. The shrink factors were then applied to compensate for the four curable resins, A2 steel and polypropylene. So they have also applied the shrink factors when they are used for the pattern making. Process was then used to build SLA patterns of the actual tool inserts in halves. They were then investment cast out in A2 tool steel. Once the tool inserts would be fitted into the injection molding machine and used to produce the plastic wiper covers. So this is where we were talking about the wiper covers. So this is how they have used wiper covers. With the application of such rapid tooling techniques, PROF was able to start durability and water flow testing 18 months ahead of schedule, and with the cost reduction of 45% and time savings of more than 40%. So they could reduce the time from 18 months, they could go ahead of the schedule, they could reduce the cost of 45 months, they could reduce the time of 40%. So all this was possible because of the rapid prototyping, so which can be used as rapid tooling. So this was the figure which shows the cover for the rare wiper. So this is the pattern generally used. So this again they will be using it for the production of the patterns of the products through the injection molding. So this is about the applications of rapid prototyping in the automotive industry. So I hope you understood all the applications in the automotive industry, and also you understood few examples. So with this, you can able to write what are the applications of RP in automotive industry with few examples. You can come up with any of the examples that we have discussed in this lecture. So with this, I conclude my lecture. Thank you very much.